July 1st, 2025. Rio Hurtado, Chile. A telescope detects something moving wrong. Not wrong like broken, wrong like it shouldn't be here. Object designation A11P, L3Z travels at 58 kilometers per second. That's 209,000 kilometers per hour. The average asteroid in our solar system, 18 kilometers per second. This thing is moving 3 times faster than anything gravitationally bound to our sun. Within 48 hours, 3 other telescope systems confirm what the asteroid Terrestrial Impact Last Alert System already knows. This object came from outside, from another star system, from interstellar space. They rename it 3I/Atlas, the third interstellar object ever confirmed, the third visitor from beyond our solar system in recorded human history. And on October 3rd, 2025, a Chinese spacecraft orbiting Mars captures it on camera from 18.6 million miles away and stitches those images into a GIF, a simple animation, 30-second exposures, a fuzzy white dot crawling across the Martian sky. But that GIF contains evidence that rewrites what we thought we knew about imaging faint targets in deep space, about interstellar comets, and about what we can accomplish when we repurpose hardware designed for one mission to accomplish something nobody planned for. If you value documented astronomy and space exploration history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the China National Space Administration's official November 5th, 2025 statement on the Tianwen-1 mission extension published on their website, and from the academic paper published in Space Science Reviews Volume 217 on March 29th, 2021, Macker Sealers, detailing the high-resolution imaging camera technical specifications written by the Heinrich engineering team led by Q. Meng at the China Academy of Space Technology. These aren't general space news sites. These are primary engineering documents and official mission reports. Now back to the information. October 3rd, Tianwen-1 orbits Mars at an altitude varying between 265 and 11,932 kilometers. The spacecraft has been operational since February 10th, 2021, 4 years and 8 months in orbit. Its primary mission? Map the Martian surface, support the Zhurong rover landing, study geology and geomorphology. The high-resolution imaging camera on board was designed to photograph bright planetary surfaces from low orbit. Resolution, 0.5 meters per pixel at 265 kilometers altitude. Focal length, 4,640 millimeters. Primary mirror diameter, 38.7 centimeters. FA number 12, field of view, 2 degrees by 0.693 degrees. Total camera mass, 42 kilograms. The camera uses an off-axis 3-mirror astigmatic optical system, carbon-based materials throughout the structure to save weight, time delay and integration, CCDs on the imaging plane, signal-to-noise ratio exceeding 100:1 for Martian surface imaging, built to capture geology, built to map craters, built to study rocks under full sunlight at close range. 3I Atlas is 28.96 million kilometers away from Tianwen-1 on October 3rd. The comet nucleus diameter, somewhere between 440 meters and 5.6 kilometers based on Hubble Space Telescope observations from July 21st and August 20th, 2025. The coma surrounding the nucleus extends thousands of kilometers. But here's the engineering problem. The camera was designed to photograph targets 10,000 to 100,000 times brighter than this comet. Mars reflects sunlight. Mars is close. Mars fills the field of view with photons. 3I Atlas is a faint smudge of gas and dust moving at 129,800 miles per hour, 58 kilometers per second in absolute terms. The Tianwen-1 orbiter itself moves at 86 kilometers per second relative velocity. You're trying to photograph a dim moving target from a moving platform designed to photograph something completely different. The math says it shouldn't work. The specifications say the camera can't do it. But early September, the mission team starts planning anyway. The team runs simulations, repeated calculations, orbital mechanics, brightness modeling, trajectory prediction. They know 3I Atlas will make closest approach to Mars on October 3rd at approximately 29 million kilometers separation. They know multiple spacecraft will attempt imaging. NASA's Mars Reconnaissance Orbiter with its high-rise camera, 50-centimeter aperture. ESA's ExoMars Trace Gas Orbiter with its Cassis camera, 13.5-centimeter aperture. ESA's Mars Express with its HRSC camera, the UAE's Hope Orbiter, and Tianwen-1 with its 38.7 centimeter aperture High-Rik, Tianwen-1 won't capture the highest resolution image. That belongs to HiRISE with its projected 30 km per pixel spatial resolution. But Tianwen-1 will attempt something nobody has tried before with this specific hardware configuration. The team recalculates exposure times. They adjust spacecraft attitude control parameters. They modify pointing accuracy requirements. They prepare the high-resolution imaging camera for an observation target it was never designed to handle, October 1st through October 4th. The observation window. Tianwen-1 captures multiple images, 30-second exposures. The camera captures photons from a target 50,000 times fainter than the bright Martian surface it normally photographs. The data transmits to Earth. Ground stations receive the telemetry. The ground-based application system processes the raw data, image by image, frame by frame, and there it is, the nucleus, the coma. The fuzzy ball of light, with a diameter reaching several thousand kilometers in the processed images. The shape elongates slightly toward the sun, not a tail pushed by radiation pressure, but a plume, anisotropic mass loss. The comet actively outgassing. Carbon dioxide, carbon monoxide, water vapor escaping from the nucleus as it heats. The team takes the sequential 30-second exposures and compiles them. They create an animation, a GIF. The comet moves across the stellar background. Stars streak behind it because the camera tracks the comet's motion. 3i Atlas crawls through the frame. Downward movement relative to the camera's orientation. The animation is crude. The images are grainy. The resolution can't match what HiRISE theoretically captured. But it exists. It works. It proves the concept. The China National Space Administration releases the images on November 6th, 2025. One standalone photograph from October 3rd, one animation compiled from the series. The announcement describes the observation as an important extension mission for Tianwen-1, a technical demonstration, a proof that the spacecraft can track and image faint celestial bodies beyond its primary design parameters. The statement explains the challenges: vast distance, high relative velocity, extreme dimness compared to normal targets, and hardware designed for completely different conditions. The team at the China Academy of Space Technology provides technical commentary. This observation maximizes the imaging capabilities of the high-resolution imaging camera while specifically targeting the faint target. Feasibility assessments involve combining orbital characteristics, brightness features, geometric dimensions of the Atlas orbit, and the technical capabilities of the orbiter's scientific payloads. The announcement states this accumulated experience will support Tianwen-2's asteroid exploration mission. Tianwen-2 launched in May 2025. Its objectives: visit a near-Earth asteroid, collect samples, return them to Earth. The technical lessons from observing 3i Atlas feed directly into planning for that mission. How to track fast-moving small bodies, how to image dim targets from spacecraft originally designed for planetary observation, how to push hardware past its nominal specifications. 4 days later, Congresswoman Anna Paulina Luna from Florida posts on social media platform X that she contacted NASA's acting administrator Sean Duffy on October 31st, requesting release of the HiRISE images. Her letter explains the scientific importance, the spatial resolution, the unique perspective. NASA responds through her public statements that they will release the data once the U.S. government shutdown ends. But during that waiting period, China's release of the Tianwen-1 images fills the gap. Scientists globally analyze the Chinese data. The nucleus appears as the bright center. The coma extends around it. The diameter measurement matches expectations from other observations. The chemical signature remains consistent with earlier spectroscopic data from ground telescopes and space observatories. What we see in the Tianwen-1 GIF confirms what we already suspected, but adds new data points. The viewing geometry differs from Earth-based observations. Mars provides a different angle. A sideways view of the coma structure, while Earth and the Sun were separated by only about 10 degrees relative to distant 3i Atlas when Hubble captured its July 21st image. 3i Atlas was first spotted as a 11PL 3Z moving through Serpens Cauda and Sagittarius near the galactic plane. Pre-discovery observations date back to June 14th, 2025, found in archives from 3 different Atlas telescopes and from Caltech's Zwicky Transient Facility at Palomar Observatory. Sam Dean, amateur astronomer, noted additional Atlas observations from June 5th through 25th. He suspected the comet wasn't discovered earlier because it passed in front of the galactic center's dense star fields, hard to discern against that background. On July 2nd, multiple telescopes confirmed cometary features. The Deep Random Survey in Chile, Lowell Discovery Telescope in Arizona, Canada, France, Hawaii Telescope at Mauna Kea, All showed a marginal coma with potential tail elongation, 3 arcseconds in angular length. David Jewett and Jane Liu used the Nordic Optical Telescope on July 2nd and confirmed clear activity. Diffuse appearance. On July 2nd, the Minor Planet Center gave it the interstellar object designation 3Ae, making it the third interstellar object confirmed after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Also designated C/2025 N1 as a non-periodic comet. By the time of official naming Tianwen-1’s, the MPC had collected 122 observations from 31 different observatories. The orbital parameters locked in: eccentricity 6.143. That's extremely hyperbolic. Compared to Oumuamua's eccentricity of 1.2 and Borisov's 1.35, 3I Atlas moves faster than both previous interstellar visitors. Hyperbolic excess velocity, 58 kilometers per second. Oumuamua, 26 kilometers per second. Borisov, 32 kilometers per second. The orbital inclination, 175.1 degrees, nearly retrograde, moving opposite to the planet's direction around the Sun. Perihelion distance, 1.357 astronomical units. That puts closest solar approach at approximately 203 million kilometers, just inside Mars orbit. Perihelion date, October 29th. 2025 at approximately 1127 UTC based on n-body integration using non-gravitational forces. The comet actively sublimating since at least May 7th, 2025, according to NASA's Transiting Exoplanet Survey satellite observations. That's roughly 6.4 astronomical units from the Sun. Most comets don't activate until much closer. This early activity indicates highly volatile compounds. Carbon dioxide and carbon monoxide sublimate at much lower temperatures than water ice. The spectroscopic observations from the James Webb Space Telescope on August 6th revealed an unusually high carbon dioxide to water ratio in the coma. The Very Large Telescope in Chile, during multiple observation sessions, detected nickel vapor. Rohan Rahat-Gaonkar and Thomas Puzia at Instituto de Astrofísica Pontificia Universidad Católica de Chile led that discovery team. Their paper published in late October described finding nickel gas at nearly 4 times Earth's distance from the Sun, where temperatures are too cold for metals to normally vaporize. Nickel levels increased as 3I Atlas approached the Sun. The nickel detection used spectrographic analysis of the light characteristics coming off the comet. This chemical signature provides clues about where 3I Atlas formed, what conditions existed in its original stellar system. What elements were abundant in that environment billions of years ago? Hubble observations from July 21st showed a teardrop-shaped cocoon of dust coming from the nucleus. Background stars streaked in the exposure because Hubble tracked the comet's hyperbolic trajectory. The image was taken when 3I Atlas sat 450 million kilometers from Hubble, 277 million miles from Earth. The bright glow around 3I Atlas in that Hubble image extended approximately 4,000 kilometers. The width displayed the lower surface brightness envelope that fainter instruments miss. NASA's Neil Gehrels Swift Observatory detected hydroxyl gas from 3I Atlas in July and August 2025. Hydroxyl is a byproduct of water molecules dissociated by sunlight. Dennis Budowitz at Auburn University led the team using Swift's ultraviolet optical telescope. Finding water signature at this distance was surprising, nearly 3 times Earth's distance from the Sun. Direct surface ice sublimation shouldn't happen this far out. The team theorized the nucleus was ejecting tiny ice-coated dust grains. These particles have larger surface area relative to volume. Faint sunlight heats them efficiently. Their icy coatings turn into gas. Water vapor production rate, approximately 40 kilograms per second. That's roughly equivalent to a fire hose at full blast. An extended source mechanism distinct from traditional sublimation on the main nucleus. The coma of 3I Atlas appears slightly elliptical. Measurements from the 10.4-meter Gran Telescopio Canarias showed dimensions of 26,400 by 24,700 kilometers, almost twice Earth's diameter. The angular diameter from Earth in July was about 2 arcseconds for the most visible part at full width half maximum, 10 arcseconds for the full extent, pre-discovery observations by the Vera Cia. Rubin Observatory showed coma growth from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. The coma contains relatively large dust grains, several micrometers in radius. The reddish color is similar to D-type asteroids, solar system comets, and 2I Borisov, likely caused by irradiated organic compounds like tholins in the dust grains. ESA's ExoMars. Trace Gas Orbiter captured 3 Atlas between October 1st and 7th using its color and stereo surface imaging system, 5-second exposures, multiple images stacked to reveal the comet. The CAS's camera has an angular resolution of 11.36 microradians per pixel. At 30 million kilometers distance, that translates to 340 kilometers per pixel. 1 to 2 orders of magnitude larger than the expected nucleus diameter. The camera detected the bright glow around 3I Atlas, extending approximately 680 kilometers, an order of magnitude smaller than the Hubble image width. CAS's could only detect the brightest region around the nucleus while missing the lower surface brightness envelope. The primary mirror diameter, 13.5 centimeters. Surface area, about 300 times smaller than Hubble's telescope mirror. Mars-Express attempted observations with its high-resolution stereo camera using 0.5-second exposures. The maximum limit for that camera? 3. I Atlas didn't clearly appear in initial Mars-Express images. Scientists continued analyzing data, adding multiple images together to see if they could spot the faint comet. The Omega and SPICAM spectrometers on Mars-Express and the Nomad spectrometer on ExoMars TGO attempted to measure the spectrum of light from 3I Atlas. Uncertain whether the coma and tail were bright enough for spectral characterization, NASA's Mars Reconnaissance Orbiter used its HiRISE camera to photograph 3I Atlas on October 2nd and 3rd. HiRISE aperture, 50 centimeters. Projected spatial resolution, 30 kilometers per pixel, approximately 3 times better than Hubble's July 21st image resolution. But the US government shutdown that began days after the observations prevented immediate data release. NASA's official website doesn't update during shutdowns. The images remain unreleased as of early November. Astrophotographer Simeon Schmaus stacked publicly available images from NASA's Perseverance rover's Mastcam-Z camera and reported a faint smudge at 3I Atlas' expected location on the Martian sky. The Perseverance right. Navigation camera captured images on October 4th. An elongated stripe about 4 times longer than wide appeared in the data. Whether those images definitively show 3I Atlas remains unconfirmed. The smearing could result from limited angular resolution and exposure time rather than the object's actual shape. Multiple spacecraft positioned throughout the solar system attempted or planned observations. The Psyche spacecraft passed 0.302 astronomical units from 3I Atlas on September 4th, 2025, 45.2 million kilometers, 28.1 million miles. The Jupiter Icy Moons Explorer will pass within 0.428 astronomical units on November 4th, 64 million kilometers. But JUICE won't return that data until February 2026, due to communication schedules and data processing timelines. Europa Clipper, Hera, Lucy spacecraft may pass through 3I Atlas cometary tail after perihelion. Potential direct observations of conditions and composition there. NASA's Parker Solar Probe, Punch mission, and ESSE, NASA's SOHO, also positioned to gather data. The Hubble Space Telescope, James Webb Space Telescope, TESS, SWIFT, SphereX all contributed observations from various distances and wavelengths. The Tianwen-1 accomplishment stands out not because it captured the highest resolution or discovered something new. It stands out because it proves adaptive mission planning works, because it shows what happens when engineering teams think beyond nominal specifications, because it demonstrates international cooperation in space science through data sharing even during periods of geopolitical tension. The Chinese team could have kept the data restricted. They released it publicly. Scientists in the United States, Europe, and elsewhere immediately incorporated the Tianwen-1 observations into their analyses. The viewing geometry from Mars provides constraints that Earth-based observations can't offer. The timing during NASA's shutdown means Tianwen-1 data fills a critical gap in the observational record during 3I Atlas' closest approach to Mars. The technical achievement requires understanding what the team overcame. The camera operates in push-broom mode. The spacecraft moves, the camera scans, time delay and integration. CCDs accumulate signal as the image moves across the detector. This works perfectly for Mars surface imaging, where the spacecraft altitude and velocity are predictable and the target is bright and stationary. For 3I Atlas, everything changes. The target moves at 58 kilometers per second. The spacecraft moves at 86 kilometers per second. The relative geometry shifts constantly. The target is 50,000 times fainter than Mars. The camera must accumulate photons for 30 seconds to build enough signal. During those 30 seconds, 3I Atlas moves across the sky. The spacecraft must track that motion. The attitude control system must maintain precise pointing. The slightest drift ruins the image. The engineering team calculated the exact pointing adjustments needed. They programmed the spacecraft to execute those adjustments during the exposure. They verified the calculations through simulation. They conducted theoretical modeling. They performed extensive instrument checks in early September. They worked out the specific observation and imaging plan based on 3i Atlas trajectory, brightness, size, and the capabilities of the orbiter's scientific payloads. The result: grainy images, fuzzy resolution, but clear confirmation of nucleus and coma, clear measurement of coma diameter, clear demonstration that the comet exhibits expected cometary behavior, active outgassing, gas and dust production, plume structure oriented toward the sun. The animation shows motion. The GIF displays trajectory. 30-second intervals captured in sequence, compiled into continuous movement. The stars streak. 3i Atlas moves against that background. Direction consistent with calculated orbital parameters. Velocity consistent with the 58 km/s hyperbolic excess velocity. Everything matches prediction. Everything confirms the comet's interstellar nature. If you value documented astronomy and deep space exploration history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. The script is researched and factual, using sources from Harvard astrophysicist Avi Loeb's series of Medium articles published between October and November 2025, analyzing the Mars-based observations, and from the official ESA statement published on their website regarding ExoMars TGO and Mars Express observations of 3i Atlas. These sources provide primary observational data and professional astronomical analysis from active researchers working on this object. Now back to the information. 3i Atlas age estimates range from 3 billion to 11 billion years, potentially older than our solar system's 4.6 billion years. The trajectory traces back toward the galactic center region when you run orbital mechanics in reverse. Where it formed exactly remains uncertain. Which stellar system birthed this comet? Which planetary disk's outer reaches contained the ice and rock that eventually became 3i Atlas? The journey through interstellar space likely took millions or billions of years. Cosmic radiation altered the ice chemistry over that time. Irradiation changed the crystalline structure. Impurities accumulated. The surface darkened and weathered. By the time 3i Atlas entered our solar system, it carried a chemical and physical record of ancient conditions from another star system and the effects of the interstellar medium during its long journey. The object's brightness evolution surprised observers. From 18th magnitude at discovery on July 1st to gradually brighter as it approached the sun, but no major outbursts detected through August. Steady activity level, steady brightness increase. NASA's Transiting Exoplanet Survey satellite data suggests activity began in early May at 6.4 astronomical units, 2 months before discovery. The comet already had a coma by then, already releasing volatiles. Most solar system comets don't activate that far out. Only those with extremely volatile ices like carbon dioxide and carbon monoxide. The high CO2 to water ratio measured by Webb supports this. 3. I Atlas contains more carbon dioxide ice than typical comets. The formation environment must have been extremely cold. Cold enough to efficiently freeze carbon dioxide while water remained less abundant or locked away in different forms. The anti-tail phenomenon observed in some images. Most comets show tails pushed away from the sun by solar radiation pressure and solar wind. 3i Atlas occasionally showed emission toward the sun, anisotropic mass loss, jets from active areas on the nucleus pointing in specific directions regardless of the sun's position. This happens when certain surface regions heat preferentially. When rotating, nucleus exposes different faces to sunlight at different times. When subsurface ice pockets suddenly breach the surface and vent. The Hubble images from July showed the teardrop shape with extension roughly opposite to projected negative heliocentric velocity in anti-solar directions, but also very faint emission in the actual anti-solar direction. Radiation pressure acceleration offers natural explanation for that component. The brighter plume toward the sun indicates anisotropic jets. The nucleus mass estimates vary. Avi Loeb calculated minimum mass of 33 billion tons needed to avoid detection of non-gravitational acceleration over 5 months. That sets the lower bound at 5-kilometer diameter, assuming typical comet density. Spherix observatory data, based on observed brightness and assumed albedo, suggested maximum diameter of 46 kilometers, wide range. Hubble observations refined the estimate to between 0.44 kilometers and 5.6 kilometers for nucleus diameter. More observations needed to narrow further. The brightest pixel in eventual high-rise images will provide tighter constraints on surface area and therefore diameter. Each additional viewing angle helps. Each telescope contributes data. The path through the solar system takes 3, I-Atlas between Mars and Earth orbits, but never close to Earth. Minimum approach distance to our planet, 1.8 astronomical units, about 170 million miles. 270 million kilometers. No threat, no possibility of impact. The retrograde orbit means it moves opposite to planetary motion, makes gravitational interactions complex, makes trajectory prediction require careful calculation. The perihelion on October 29th at 1.357 astronomical units, 130 million miles from the Sun, 210 million kilometers, just inside Mars' orbit average distance. The Sun deposits gigawatts of power on 3 I-Atlas surface during close approach. If it's a natural comet with typical structure, it might erupt in flares or fragment into pieces. Comets sometimes break up during close solar passes. The heat stresses the structure. Temperature gradients crack the nucleus. Trapped volatiles burst out violently. 2. Borisov showed signs of fragmentation during its solar approach. Oumuamua showed no such activity, but wasn't clearly a comet. 3. I-Atlas behavior during and after perihelion will reveal structural information. Will tell whether the nucleus is consolidated or loosely bound. Will show whether volatile distribution is uniform or concentrated in pockets. Post-perihelion observations became difficult from Earth. The comet's position put it behind the Sun, as viewed from Earth during late October. Minimum angular separation between the Sun and 3 I-Atlas, 2.59 degrees on October 21st, when the comet was 2.4 astronomical units from Earth. Too close to the Sun's glare for safe observation from most ground telescopes. Space telescopes like SOHO with coronagraphs could potentially track it during that period. But detailed observations had to wait until 3 I-Atlas emerged from behind the Sun in November. Amateur astronomers captured images from Earth starting in early November. Inverted time-lapse from Leander, Texas, United States. On November 10th, used a Celestron RASA 11-inch telescope and ZWO ASI 2600MC Pro camera. 60-second exposures, stacked and inverted in PixInsight software to highlight the faint coma and dust tail after perihelion. The comet survived. No fragmentation detected. Brightness evolution continued as expected. The coma remained intact. The nucleus held together. Now the comet moves outward, away from the Sun, back toward interstellar space. Its hyperbolic trajectory ensures it won't return, not in 1,000 years, not in 1,000,000, not ever. 3 I-Atlas will exit the solar system, will slow down as solar gravity pulls back on it, but never slow enough to be captured. The hyperbolic excess velocity of 58 kilometers per second means even at infinite distance from the Sun, the comet will still move at that speed relative to the solar system. It will re-enter the interstellar medium. Will travel for millions or billions more years. Might eventually encounter another star system. Might pass close enough to another planetary system for their astronomers to detect it. Will carry with it the physical record of its journey through our solar system. Solar wind particles implanted in surface layers. Cosmic ray exposure from our Sun added to earlier exposure during its interstellar journey. Chemical changes from our Sun's heat and radiation. Future alien astronomers studying 3 I-Atlas millions of years from now will read that record and know it, once passed through a system with a G-type main sequence star and 8 major planets. The Tianwen-1 GIF becomes a historical artifact, the first animation of an interstellar object captured from Mars orbit, the first demonstration of Chinese deep space assets tracking a hyperbolic visitor, the first time this specific camera configuration successfully imaged such a faint, distant target. The images have limitations, grainy, fuzzy, low resolution compared to what high-rise theoretically achieved. But they exist, they're published, they're analyzed. They contribute to the global scientific understanding of this object. They demonstrate China's growing capability in interplanetary exploration and adaptive mission planning. They show that space science advances through international efforts, even when politics creates friction. The Chinese team shared data. Scientists everywhere incorporated it. Knowledge increased. Understanding deepened. The technical lessons feed forward. Tianwen-2 will benefit. That mission targets near-Earth asteroids, small bodies, faint at times, fast-moving relative to the spacecraft. The experience observing 3 I-Atlas teaches exactly what Tianwen-2 needs to know. How to track small, fast targets. How to adjust camera parameters for faint objects. How to process data when signal is weak. How to extract maximum information from limited photons. The Tianwen-2 mission launched May 20th, 2025. first asteroid encounter scheduled for 2027, sample collection from the surface, return to Earth by 2030 or 2031. The 3I Atlas observation in October 2025 happens between Tianwen-2 launch and its asteroid encounter. Perfect timing to test techniques. Perfect opportunity to validate procedures. Perfect chance to train the team. ESA's Comet Interceptor mission waits in the future. Selected in 2019. Launch planned for 2029. The concept: park a spacecraft at the Sun-Earth Lagrange Point 2. Wait there. Monitor for a suitable target, a pristine comet from the distant Oort cloud, or, unlikely but highly desirable, an interstellar object like 3I Atlas. When a target appears, rapidly redirect the spacecraft, intercept the object, deploy multiple probes, study the visitor up close from multiple angles simultaneously. The mission design assumes discovery will happen with enough warning time to calculate an intercept trajectory, assumes the target will have favorable geometry, assumes technology will work as planned. Each interstellar object discovered refines those assumptions. Each observation campaign identifies challenges. 3. Atlas showed how quickly these objects can approach and recede, how international coordination happens or fails, how quickly data must be shared to enable follow-up observations, how diverse the interstellar population appears to be. Oumuamua looked inactive, possibly an asteroid fragment. Unusual shape, pancake or cigar, tiny. Borisov looked like a normal comet, similar to solar system comets. Nucleus a few hundred meters, active coma and tail. 3 Atlas shows intermediate behavior, active like Borisov, unusually high volatiles for the distance. Chemical composition different from typical comets. Size potentially much larger. Each visitor teaches different lessons. Each expands the sample size of known interstellar objects from 1 or 2 to 3 to eventually dozens. The statistical implications matter. Before Oumuamua, we had 0 confirmed interstellar objects. Theoretical calculations predicted they should exist. Models suggested 1 or 2 should pass through the inner solar system per year. Most too faint to detect, most moving too fast to observe closely. The Atlas survey discovered 3I Atlas. Atlas telescope array designed specifically to find fast-moving objects, multiple telescopes at different locations. Automated detection algorithms, rapid follow-up procedures. The system works. The 4th interstellar object will be discovered, the 5th, the 10th, the 100th. Each discovery refines population statistics. Each object constrains formation models. Each visitor provides 1 more data point about conditions in other stellar systems. 3I Atlas, with its high carbon dioxide ratio, suggests formation in a cold outer region. Maybe around a star less massive than the Sun. Maybe in a system with different volatile distribution. Maybe ejected from its home system billions of years ago by gravitational interactions with giant planets or passing stars. The isotopic ratios would tell more. The detailed chemical fingerprint would reveal formation temperature. The nuclear composition would indicate what elements were abundant in the original stellar nebula. Some of that data already collected. More analysis ongoing. Papers will publish over the next year detailing every measurement. The Tianwen-1 observation window lasted 4 days, October 1st through 4th. The spacecraft captured images on October 1st, 2nd, 3rd, and 4th. The team selected the October 3rd image as the best standalone photograph, clear nucleus, clear coma, good signal to noise. The animation compiled images from across the observation period, sequential frames showing motion. The GIF loops endlessly. 3I Atlas moves down through the frame. Stars streak behind. The comet's fuzzy light remains constant. No obvious brightening or dimming during those 4 days. No outburst, no sudden change. Steady activity. Steady appearance. Exactly what you expect from a comet at that distance, steadily sublimating volatiles as it approaches perihelion still 3.5 weeks away. The ground-based application system processed data and generated images using standard procedures. Photon counting, background subtraction, flat field correction, bias frame removal, dark current subtraction, stacking of multiple exposures where applicable. The processed images show the comet as a fuzzy white blob. The coma appears roughly circular in the lower resolution Tianwen-1 data. Can't resolve the teardrop shape Hubble saw. Can't see the anti-tail structure. Can't distinguish different regions of the coma, but can clearly measure the overall extent. Can confirm the comet exists at the predicted location, moving in the predicted direction at the predicted brightness. Can verify the object behaves like a comet with active gas and dust production. Can demonstrate that observations from Mars orbit successfully captured it. The comparison with other Mars-based observations matters. ExoMars TGO with CASES captured similar images. 5-second exposures instead of 30 seconds, smaller aperture. Comparable results: fuzzy blob, clear detection, motion across stellar background. Mars Express couldn't clearly detect it with 0.5-second exposures. Too short. Not enough photons. The expected high-rise data from Mars Reconnaissance Orbiter will have better resolution. 50-centimeter aperture versus 38.7 centimeters for high-RIC. Better optics, better detectors, better signal processing, but unreleased during government shutdown. When those images finally publish, they'll show 3-eye atlas in higher detail. We'll resolve more coma structure, we'll measure brightness distribution more precisely, we'll provide better size constraints, but they won't show anything fundamentally different. Won't reveal 3. Eye atlas as anything other than what it appears to be, an interstellar comet actively outgassing as it approaches the sun. Some speculation suggested 3-eye atlas might be artificial, might be a probe from another civilization. Harvard astronomer Avi Loeb published papers exploring that hypothesis, listed anomalies that could potentially indicate technological origin, size much larger than previous interstellar objects. Brightness evolution possibly inconsistent with simple comet models. Direction of arrival roughly aligned with the WOW signal direction from 1977. Chemical composition unusual compared to solar system comets. All valid observations, all worth investigating. But every measurement so far points to natural comet. Spectroscopy shows gases expected from sublimating ice, dust production rates match comet models, no radio emissions detected. No optical signals beyond thermal glow and reflected sunlight, no maneuvers, no course changes beyond those explainable by outgassing thrust. Trajectory follows hyperbolic path determined by solar gravity and modest non-gravitational acceleration from jetting. Behaves exactly like a comet should behave. Looks exactly like a comet should look through telescopes. The hypothesis that it's artificial remains possible but unsupported. The evidence favors natural origin from another star system's outer planetary region or Oort cloud equivalent, a lump of ancient ice and rock ejected billions of years ago. Now passing through our neighborhood on its way to somewhere else, the Tianwen-1 images and GIF fit into that evidence base. They show nothing unexpected, nothing anomalous, nothing that contradicts the comet interpretation. They show a fuzzy ball of light with surrounding coma, gas and dust production, motion consistent with calculated trajectory, brightness consistent with predicted solar heating and volatile sublimation. The images are valuable because they exist, because they fill gaps in observational coverage, because they demonstrate technical capability, because they add data points to the record, not because they reveal something strange or unprecedented. 3. Eye atlas is strange by virtue of coming from another star system, but its behavior within our solar system appears entirely normal for an active comet. The global observation campaign continues past perihelion. Ground telescopes track 3, Eye atlas, as it becomes visible again from Earth in November. The brightness evolution post-perihelion constrains models of nucleus structure and volatile distribution. Did the close solar pass trigger outbursts? Did surface layers strip away exposing fresh ice? Did temperature gradients crack the nucleus? Observations from mid-November and December will answer those questions. The comet will gradually fade as it recedes from the sun. Will become too faint for most telescopes by early 2026. The largest observatories might track it into mid-2026. Then it vanishes. Too far. Too faint. Gone back into the darkness from which it came. But the data remains. The measurements persist. The images stay in archives. Scientists will analyze 3 Eye atlas data for years. We'll compare it to future interstellar objects. We'll refine understanding of the interstellar comet population. We'll use it to calibrate detection systems and plan observation strategies for the next visitor. The timing of 3 Eye atlas discovery and observation illustrates progress. Oumuamua discovered in October 2017 after closest solar approach. Already moving away. Only a few weeks to observe before it faded. Astronomers caught it leaving, couldn't prepare, couldn't coordinate complex observation campaigns. Got what data they could with available instruments. Many questions left unanswered. Borisov discovered August 2019 while approaching. 3 months before perihelion. Time to prepare, time to coordinate. Time to point multiple telescopes. Better observations, more data, more detailed measurements. 3 Eye atlas discovered July 2025. 4 months before perihelion, even more preparation time. The Mars flyby in early October provided unique viewing geometry. Multiple spacecraft positioned to observe, international coordination despite challenges, government shutdowns, bureaucratic delays, but data collected, data shared, data analyzed, Each interstellar object discovered earlier in its approach, each observed more thoroughly, each understood better. The trend continues with improving technology, better surveys, faster detection algorithms, more sensitive cameras. The next interstellar object might be discovered 6 months before perihelion, the one after that, a year before, eventually early enough to launch a dedicated probe to actually visit an interstellar object up close, to touch material from another star system. The Tianwen-1 GIF loops, the comet moves, the evidence accumulates. 38.7 centimeter mirror collects photons from 18.6 million miles away. 30-second exposures capture faint light from ancient ice. Chinese engineers push spacecraft past design specifications. International scientists share data across political boundaries. Humanity collectively observes visitor from beyond our solar system. The images are grainy. The resolution is limited, but they work. They prove the concept. They advance the knowledge. They document history. October 3rd, 2025. The day a Chinese spacecraft at Mars captured an interstellar comet in motion, created a GIF that shows photons from another stellar system reflecting off ice that formed in conditions we've never seen. The evidence that matters? It happened. We captured it. We shared it. We learned from it. And somewhere in the data, buried in those fuzzy pixels, lies information about star formation and planetary system evolution and comet composition and the nature of material in the interstellar medium, and how objects escape their home systems and what happens to them during billions of years traveling through the void between stars. All there, waiting for analysis, waiting for understanding. The GIF loops, the comet moves, the evidence remains.